Okay, if you understand this first question in terms of what's going on in terms of forces and velocities, you've got a reasonable understanding of the kind of core of projectile motion. So if you recall, we tend to ignore the air resistance, which is the force that has an effect on the ball going, horizontally. And yeah, there's air resistance with it dropping as well, but we just ignore that. And anyway, so there's that. So once the ball is actually kicked, there really is only one force operating on that, and that's gravitational force. And the vertical velocity, if you recall, we divide this initial velocity, which is at this angle, into a vertical one, which affects how high it goes, and then one to the side, which is how far it goes in terms of range. And when it gets to the top, at the peak, it's at 0 meters per second in terms of vertical velocity, although it is still traveling horizontally at that stage. Because as it goes up in the air, it gets slower and slower and slower until it's at the peak, and then it speeds up as it comes to the ground. Anyway, on with the question. If we're looking at the force at C and G, they're on either side of this equally, but really it doesn't matter because at every single point here, the gravitational force will be the same. So I should take care to draw those arrows a fairly similar size. It's not perfect, I know, but we'll get over ourselves and move on. The horizontal component of the velocity at B and H. Now that also is something that stays the same, and it stays the same because there's no drag or air resistance, so it's in that direction. And yeah, it's not a great one, but those arrows should be the same size, so that's not great, is it? And then we're looking at the vertical velocity at D and F, and notice they're on either side. Now going up till E, the velocity is always in this direction, and after E, the velocity is always in that direction. So when we put this velocity in, if I draw it like that, God, it's not great, but anyway, if I draw that, I have to draw it an equal arrow showing the velocity going down on that side. And that would be the arrows for those. A little bit confusing in terms of my drawings, but that's how they work. Now I did this earlier, but for some reason the recording didn't stay recorded, and I'm redoing it. So I've already kind of started doing the calculations on this, and this is a typical thing with projectile motion. You've got a particular velocity that it's going up in, you've got an angle, and you want to know the horizontal velocity that way, which is going to tell you how far it goes, and then the vertical velocity, which is going to tell you how high it goes. So we separate that up. So in order to work out the horizontal one, if this angle is 42 and that's 16 meters per second, we're going to be using cos because this side here is adjacent to that angle there. It's cosine is adjacent over hypotenuse. So that's going to be cos 42 over the adjacent over the hypotenuse, which is 16. We rearrange it, so 16 gets multiplied by cos 42. Hoping you're comfortable with that, and that gets 11.9. Now, if this was a straight out answer, I would do that to two significant figures, because that 16 there tells me it's only 2SF, and that would be 12 meters per second, but I'm going to leave it there at 11.9 at the moment. Now for the vertical velocity going up, it's on the opposite side to this. So it's going to be sine 42 is opposite over hypotenuse. So it's going to be 16 times sine 42, and I get 10.71. So those velocities are fairly close, which you'd kind of expect, because that's getting close to 45 degrees. We would expect these numbers to pretty much be the same. Okay. Anyway, so that's horizontal and vertical components. Now, it's asking about the ball at position E. Now, position E is at the peak. It's also known as the apogee. And at that point, the ball is still moving in this direction. It's still going that way. When you pick a ball, it keeps on going. But the vertical velocity at that point is exactly equal. It's where it shifts from going up to about to go down. Okay. And if you recall, gravitational force is there the whole way. The weight force is acting on it. And there is no horizontal force acting on this because we're ignoring air resistance to be negligible. So that would mean that our distance calculation this way is going to be slightly out when we calculate it because we're ignoring air resistance. Anyway, so when we talk about that, at the peak, let's get rid of that, sorry about that. At the peak, the vertical velocity is 0. As gravity is I should have just said as the gravitational force is acting on the ball. It's the only force acting on the ball. And the ball's initial velocity is slowed under the influence of gravity until it's 0 at the peak. The horizontal direction, there is no E resistance, so there is no force acting on it. And the horizontal velocity won't slow down, so it stays at 11.9 meters per second. So at point E, it is 11.9 meters per second. Okay, so it stays constant the whole way until, of course, it hits the ground. Now, calculating the horizontal distance. Now, remember, when you're looking at this ball going like this, the horizontal velocity, which is 11.9, we need to work out the horizontal distance. So we need that. And we need to multiply it by how long it was in flight, so the time in flight. But when we work out the time in flight, we need to know how long it was in the air for. And how long it was in the air for, which is going up and down, is determined by the vertical velocity. So we write down the information we've got. We've got the initial velocity, which is 10.71, the vertical velocity. Remember, do not use the horizontal velocity at this point. The final velocity at the peak is 0, and acceleration due to gravity is minus 9.8 meters per second. We don't need distance, but we do want to work out time. So when we look through the formula, we're looking for one that doesn't have d. When we do that, we find this one, Vf equals Vi plus At. So we put in 0, 10.71. It's going to be minus 9.8 because acceleration is negative. And that's supposed to be times by time, which we're trying to find out. Now the minus can go over to this side, but I'm going to rearrange it the other way, where 10.71 goes to that side, and that just becomes, so they both basically become positive. 10.71 divided by 9.8 will give you the time, and that's 1.09. Notice I haven't rounded it at this stage. It's going to be multiplied by 2, and that's because I don't want, sorry, that keeps popping out. I don't want rounding errors. So that's 2.1857 seconds. I'll multiply that by the horizontal velocity now, so now that comes into play, and that gives 26 meters, which is the final answer to 2 significant figures. And that's question 1.